Alrighty, good morning, guys. Can you hear me? How are we all doing? We're getting towards the end of the course, and there's only one more topic that we have to cover. But before I start today's lecture, I want to see if there are any questions about the material we've been through the last few weeks. There's a question. Richardson extrapolation. Yeah, we can do that. So this is a trick that's that is whenever you perform numerics, there's always this order. There's always this order of your method, like how fast does it converge? And Richardson extrapolation allows you to do two things. It allows you to estimate that order, and it allows you to speed up your already existing numerics quite easily. So the Richardson extrapolation, we talked about that, I forget how many lectures ago, 2-3 lectures ago. And so the point is that you have, so for Richardson, then you have, there is a, you want to compute A, you want to approximate a quantity A by A of H, where H, this is typically a discretization parameter. And so you want to see how good is your this one here is this is the correct one, and this one here, this is your numerical one, numerical approximation. And you want to know, like, how close are they to each other. And so if you're talking about orders, we would take the difference, and we say that difference is, say, less than a constant C times, and then the parameter, the discretization parameter, to some power K. And what we're interested in is, of course, this value of K, right? So what you want to do is you want to estimate K. That's one thing, and then you want to improve. So say, for example, you want to make it such that A minus and then something here we could call A Richardson, that this would be less than CH to some other parameter, which is better. For M bigger than K. So what Richardson does is it allows you to create this quantity here, and it allows you to estimate this K here. Are we good so far? So anyone says yes, and so then what are the formulas? So we need formulas for these two quantities, and so that's what we derived a number of weeks ago. Do you want me to rederive the formulas, or do you want me to just state them? if I can find them. So what we do is we have these, we imagine that we have a sequence. We have a sequence of AHs. So you have A of H1, A of H2, H3, and so on. And these H's, ordered. You have that H1, this is equal to 2 times H2. H2 is equal to 2 times H3, and so on. Right, so H3 is like half the size of H2, and so on. And so one thing we did was we expanded AH. It's always a Taylor when you do this stuff, into a Taylor. So we would write something like A of H, this would be the correct value. And then it'll be, if we have a k-order method, then the next term in the Taylor would just be this one with the k. So there'll be some coefficient, ak h to the power k. And then there'll be the next one coming up would be a higher power here, and then we call it higher power m. M is typically k plus 1, but it doesn't have to be. So then you have hm here, and then you'll have some higher order terms. This would be, say, h1. And then this will be O of h1 to the next one on. And you would do this for all of them. So you have the same thing for h2. So on. So one thing you get out from all of this is you get a formula here for A. You get something like, let me just, you said just state it, so I won't derive it, but one thing we derived a while back was a formula of this type here, divided by 1 minus 2 to the k. And then there will be a coefficient here that would have to do with, there will be some coefficient times h2 to the m plus O of h2 to the m plus 1. So you see, we got an improvement, right? We got an improvement, this one here, this, instead of using h1 to approximate this one here is better. Yeah, because it gets rid of it gets rid of the kth order. Right. If I were to use A of h1, the approximation here would come, there will be of a kth order, but if I, instead of h1, I combine these two into this ratio, the next order up will be m. You can also turn this thing into, right, so that's what I mean here by improving it. This term here, this is my Richardson extrapolation improvement. This is A rich of, say, h2. And it gives me a higher order. To get the estimate of k, we needed 3, and we can get the estimate of k by taking this ratio h of h1 minus a of h2 divided by a of h2 minus a of h3. This is going to give you 2 to the k. So if I can compute this I have this sequence, I take this ratio, I take log, and I'm going to get the order k. So we did an example in class not very long ago. Maybe I can pull that up again. We can look at it one more time. So we did a Richardson extrapolation example here. So here we have my, this is my matrix A for different values of this. Right, so can you guys see my MATLAB screen? Is it visible to you? Okay, so we have this sequence of numbers, right? So for each of these ones here, there's, how many are there? 1, 2, 3, 4, 5, 6, there's 7, right? So I have H1 up to H7. And the first order of business is figuring out what the order is. And so that's where we took the ratio of these three, and then we took log. So that's the first order of business. And then the next one is to extrapolate. Right, so extrapolation means that we want to improve these numbers up here. So you can see the code is, first you have to estimate the order. Okay, so let me try to run it. Lecture 11. So here it runs. First it estimates the order, and you can see the order comes out to be, well, 1. Maybe I should make the digits a bit more precise. Again. So you can see the order converts to something that is very close to 1. And so when you do the extrapolation, you need to know what the order is. So first you estimate the order. Okay, so that's what we have here, k is equal to 1. And then the extrapolated values for A was given by that formula we had before, like that difference, and then divided by this 1 minus 2 to the power k. And now you insert that k that you found from estimating the order. And then you do the extrapolation, that is, you improve these numbers you have up here. And so that's what you're seeing at the bottom part. This is what you're seeing from here and then down to here. Does that make sense? What are those numbers? This is from an example. This is from an example that we did last time. We performed Richardson extrapolation on it. What the precise numbers are, this to do Richardson, the only thing you need to know is that these numbers, they come out from some numerical method, and every time you go from one to the other, that the precision parameter has doubled. I think the numbers here, they came out from a PDE that we solved last time. We solved the PDE using this code here. Yeah, we did a PDE solver last time where we had this was it the implicit method we did? I think it was the implicit method we did. So this is where these numbers are coming from. I think I had there, when you do the PDE, you have a time variable and you have a spatial variable. And what we did was we fixed the spatial grid. So we had X, the X variable is fixed to have 10,000 points. And then what we do is we increase the number of time steps. And then we estimate how this PDE method, the implicit method, what order it has as the time discretization improves. So when I run this code here, you'll see these numbers. So if I go up to format, PDE, this one here. Right, so those were the pictures we looked at last time, and the numbers you're seeing coming out here, these are these numbers we had from before. So I think I went from I started out with 100, and then I doubled every time. So we see the first number is this one here, and then I do the next one. The next one will be 200, and I get an improvement, and so on. And I think I end up with the last number I did was like 6400, and that's that number that you saw before. Yeah. Other questions or comments? Brody and Glasserman. Okay, so then this is a while further back. Let me look up when that was we talked about that. So this is syllabus. So we'll pull the syllabus and we'll see when is Brody and Glasserman. So somewhere around here we'll find Brody and Glasserman. This is when we did when we estimate the portfolio sensitivity. This is this one. So this was back on March 4th, Brody and Glasserman 96. So let me talk a little bit about that. I'll just get my own notes out. So Brody and Glasserman, there are a number of methods to estimate the Brody and Glasserman, there are a number of methods to estimate the portfolio that the replicating portfolio. So let me just briefly recall what we just been talking about. so the replicating portfolio so this is what should I denote by theta. So we interested in this object here, such that what? Well, I want my wealth. I want my wealth at time t to be the expectation under the risk neutral measure of, if it's a put option like what we're dealing with here, this is what I want. So on the right hand side, this is where I have my Q martingale. This is my Q martingale, and this is the thing that is equal to this is this f of t and st, provided that st is Markov. So if you say that, say we have a Black-Scholes model here, so say that R is 0, say that ds is equal to st sigma dBTQ. So it's a Black-Scholes model. Like the one that you're dealing with in the homework. Sometimes there's a non-zero interest rate, then you have to put a drift here, which is R times S dt, but let's just keep it simple and take R to be 0. So what I want is, I want this replicating portfolio, and the link between them is that if I take dx, this is going to be equal to theta and then ds. So this is going to be theta s sigma dBt. And then on the other hand, this is a martingale. So this is also going to be equal to F2, the derivative with respect to the second entry, evaluated at TST, and then ds. That's the Ito's lemma, right? There'll be no dt terms because it's a Q martingale. And so you can plug that in, and you'll get that this is F2 TST, and then the same thing, ST sigma dBTQ. And then you match up. So F2 is T, this is exactly my theta, right? That's the formula for the replicating portfolio. So, so in your homework, right, you're computing what this is. So in homework number 5, you find, you estimate this f of t and x for a grid, say t is in t is 0, delta t, 2 delta t, and so forth. And x is in, what should we call it, xl. This is probably going to be 0, and then it's xl plus delta x all the way up to xh. So you estimate what this is, and of course, by estimating what f is, you can also estimate what the derivative is with respect to the x variable. And so you can estimate what this thing here is. That's what you do using the PDE method. And let me just bring up the homework so I can point to it. This is not what Brody and Glasserman is about. Put that somewhere. So homework 5. So we have this f that we're hunting. That's what we create up in the first question. And then you extrapolate, this was the second question. And now we want to estimate this initial replicating stock position. So we do that, you can do that simply by estimating the derivative with respect to the x variable of f. But of course, you can also do it based on Lec12's formula, because you have the Lec12's formula, so you can compare it to that. And you can also compare it to Brody and Glasserman's two methods here, the pathwise derivative and then log the likelihood ratio. And this is based on Monte Carlo simulation. So there are 4 ways now here to estimate this initial portfolio. And so let me talk a little bit about Brody and Glasserman. So Brody and Glasserman says, well, one of them is, so this is back again, this is before spring break, that lecture on Brody and Glasserman. They have the pathwise derivative. This is to use, you want to use Monte Carlo simulation to simulate the initial positions theta 0, right? That's the one you need here, right? So the initial position, this is, you need to compute the second derivative, then evaluate it at the initial stock. And this is going to give you the initial, this is the initial stock holdings to replicate the put that pays out K minus S capital T at the end. So if you have the function f, then you can take, you can estimate the second derivative, of course, by taking difference quotients. So what is being asked, what you're being asked to do is to use other methods to do it as well and compare. Right, so the pathwise derivative is you're looking at an expectation of st minus k positive part on the q. Right? This here is your f 0 s0. And you're interested in the derivative with respect to s0. So what you do is you take the derivative of this expectation and you just move that derivative inside. I hope that you can do that. Of st minus k. So it's true that this is not a smooth function, but it's only when st is equal to k that there's a kink. So hopefully this is not, the mass of that is going to be 0. And so you take the derivative, and the only place you're going to get something. Oh, now I'm doing it for a, and this one here is for a call. I switched the k-ness, this here is for a call. I'm sure you can adjust this to switch st and k in the right order. So you take the derivative here. So this only works when st is big. So when st is big, you're going to need the derivative of st. So remember in Black-Scholes that when you have dst is equal to sigma st dbtq, what that means is that st is the initial value, and then this exponential sigma btq minus 1/2 sigma squared t. So when you take the derivative with respect to s0, you're just going to get this e sigma derivative with respect to s0. You're going to get, like the s0 goes away, you just have this coefficient, the exponential. So you'll have to plug that in here. That'll be e sigma btq minus 1/2 sigma squared t. That's your derivative, right? And this is something you can simulate. This here you can use simulation to estimate. Does that make sense? And Jan, does that make sense? This is the pathwise derivative, yes. Yep, that's the pathwise derivative. And so you simulate this random variable here, just as if you were to use simulation for simulating the call price, you would be simulating this random variable, right? And you'll take an average, and you'll provide confidence intervals and so on. Now we just simulate this random variable, take the average, and report confidence intervals and so on. Are we good so far, or are there any questions on the pathwise derivative for Brody and Glasserman? So then there was a question about the likelihood. So the likelihood, we did both these methods in class. So the likelihood, but we'll do them again. It's not a big deal. Do the likelihood. So this is again Brody and Glasserman. It's a I mean, I forget what date we did them, and but we can look up the syllabus, and it will say there when we did them. We did we did this analysis on March 4th, Brody and Glasserman. Yeah, unless my recording here is incorrect, we did it on March 4th, but we can just recall it again. So the likelihood ratio it's also a method for developed by Brody and Glasserman. I think that paper came out in 1996. By Brody and Glasserman over at Columbia. The likelihood ratio. So there, what we do is, it's again this expectation we want to get our hands on. We want to get our hands on this expectation and likelihood. Okay, so now we're gonna rewrite this expectation. We can write this out over ST's density on the cube. Right, so here what we're using is we're using the probability that ST is less than X. And then we're using a derivative with respect to X. This is going to give us the density. This here is going to be my G of X. Okay, so the derivative of the stock under the risk neutral measures distribution, I can express this expectation here by an integral over, well, in this case, STs are positive, so I'll integrate from 0 to infinity. Of X minus K positive part, G of X dx. And so what I want to do is, again, I want to compute the the derivative, because this is what will give me, I need to compute this derivative. So this thing here, this depends on the initial value S0, right? Because ST what is ST? ST was this Q of ST less than X. This would be, we insert the formula, it was S0 e to the sigma B TQ minus 1/2 sigma squared T, right? You want this to be less than X. And I'm trying to get my hands on what G here is. So I can write this here as, I move all the stuff to the right-hand side as much as possible. S over, it'll be X divided by S0. And then I'll have sigma BTQ is less than, so I moved S0 over, I move 1/2 sigma squared T over, I take log, I get something like that. And what else will I do? I'll need to have a standard normal here. So I have Q, I move sigma and square root over, square root T. This is going to be less than what I have here, divided by, well, it'll be a sigma square root T. Right, and this is the standard, this is standard normal. This quantity here, this is standard normal, mean 0, variance 1. That's why we divided by square root T. So this here is N, the normal distribution, evaluated at log X over S0 plus 1/2 sigma squared T divided by sigma root T. And this is the normal distribution. So N of X, this is 1 over root 2 pi e to the minus, there's an integral, minus infinity to X e to the minus 1/2 y squared dy. So you can see now you can see now like I'm only interested in the derivative here. So I'll take the derivative. It's going to be taking the derivative of this thing here with respect to x. That's going to be my g out here. And you can see it depends upon S0 because S0 is right in here. Right? So we get g of x. Right? So again, g of x is defined to be the derivative with respect to the initial stock price of this probability. This is the density. Right? This is going to give me, I need the derivative of this thing here. This is going to give me n prime of whatever I have inside. So that's log x over S0 1/2 sigma squared t divided by sigma root t times the derivative of what's inside. This is going to be, what will it be? It'll be log x, that's 1 over x. And then it's sigma root t. This here works when x is positive. After all, ST is a geometric bounding motion, so we're only interested in this for x positive. So that's your derivative, that's your density, and you can see that the initial value appears inside there. So what we're interested in now, I'm interested in the sensitivity of the left-hand side, right? So there's an S0 sitting in here. I'm interested in the derivative of this thing, and I can use this formula here to get the get an expression for it. So the log likelihood method says that oh, I'm going to take a derivative in this formula here with respect to the initial value. And again, blindly pull this derivative inside, even though it's not always allowed. So what you need here is, you need you need to put this monstrosity, this thing here, you need to put that in there. So again, taking the derivative of this object here with respect to S0. And how would we go about doing simulation? Well, let's see. To do simulation, I need to write the right-hand side as an expectation. So if I look at something like, I want to have a g here. So if I look at the derivative of, say, log of g of x, if I take the derivative of this thing, then I will get what? This will be 1 over g of x times, and then the derivative with respect to S0 of g of x. So this expression here, if I move this to the other side, I'll get that derivative that appears up here. I can express it as g of x times the derivative with respect to S0 of log g of x. Right, so I can plug all that mess into this formula up here. So I can plug it into this formula here, and I'll get that this is an integral from 0 to infinity. And then I'll have x minus k positive part, but instead of that derivative, I'll put in this g of x, and then the derivative with respect to is 0 of log g of x dx. And the reason I did that was that g of x is again a density. G of x is again a density, so I can write everything here as an expectation under Q, and then x becomes st minus k positive part, and then I have the derivative with respect to the initial value of log of st. Sorry, there's a g missing. This is g of st. This is log g of st. And so this is again that derivative that we're hunting can be expressed as an expectation of a random variable. And this here you can use Monte Carlo simulation to estimate. And so in the first method, the thing that you need to estimate is you need to estimate this expectation, right? So you sample what you have inside sufficiently many times, take the average, and that will give you an estimate for this expectation. And the second thing, the second method is quite similar in some ways, but it's a different quantity that you estimate. It's a different quantity that it's a different random variable that you simulate, and then you take the average. But of course, in the end, you should get similar things. Are there any other questions or comments on? So we have two ways of doing this derivative using simulation. We have two different expectations that we can use. So we can simulate each one of them, compare them, see which one is more accurate. We have the closed form expression for what it should be using Black-Scholes formula. And we also have the PD solver solution, and then there are two other ones here. It's always a lot more tricky to estimate these derivatives than it is to estimate the function itself. So Enyan, did this help? Okay. Are there other questions? Any other questions before we start? Okay, so today is going to be, as I said last time, today is going to be a short lecture. We end around when we normally take a break. So, so it's going to be a short lecture. So the last topic is the American options. Last topic is American options. And some of you, I spoke with Professor Pham a few days ago last week, and he said he's also covering some of this material in his class, and that's great. There'll be some overlap. So this here is so we're gonna have there's gonna be Shreve's chapter, and then there are going to be some notes or problems on Canvas. What I had in mind is that this is what we'll do today. This is today, and then Shreve's chapter. This is next time. Let me just show you these Canvas problems so you can see what I'm talking about. we're done with the syllabus. Let's go into Canvas. So you go here in April, there's a PDF file called Stopping Times. This is a collection of 20 pages of problems related to stopping times. I've used these problems in various courses in the past. So there's a lot more than what we need. But if you find these stopping times confusing or difficult to work with, there are lots of problems here, and there are solutions towards the end. So this is one way to get a little bit more comfortable working with these stopping times. Okay, so if you haven't pulled it already, this is 19 pages of old exam questions on stopping times that have been used in various master courses before, and they all solvable based upon the material in Shreveport. So we're going to be looking at some of them today. We're going to be looking at the ones that are the most relevant for us and these American options, and then the next time we'll switch to the chapter, so there'll be some overlap with what you've seen. There'll be some overlap with 622, and also if you've been in 485, I can see Amy and Alice are here. Depending on who you had for 485, you may or may not have seen this material in continuous time math finance. So there'll be some overlap potentially with what you already know. I hope that's okay. But then what we will be doing is we'll adjust the PDE solver. We'll adjust the PDE solver to cover American options. And this is kind of a miracle that there's a way to do this. That's so easy. There are very few. There's just a teeny adjustment needed to solve homework 6 using homework 5. So you are it's just a teeny adjustment needed, and this is this trick of it's called Brennan and Swartz algorithm. It is just a teeny tiny trick that you need to adjust homework 5. Teeny tiny adjustment you need to perform in your code for homework 5, and then you'll get homework 6 out more or less for free. The thing that is ultimately coming is a way to use Monte Carlo simulation to price Americans. And that's a different ball game. What we want to be spending time on today and next time will be these two topics, and then the last lecture we'll talk about how to use simulation to price American puts. This one here, this is an optional problem on homework 6. So let me just go over that in so you can see it. If you pull the homework that is related to American options, this homework number 6. You pull that one. The first problem here, what I'm saying is that there's going to be an interest rate, so you have to adjust your code to include an interest rate. But solving this American feature is not going to be very involved, because there's this trick of Brennan and Swartz, which we're going to be covering next time. So this problem here, the first one, it looks elaborate, but it should not be that bad. And then the second problem, this is the simulation that's based on this Longstaff and Swartz regression method. That's what the last lecture is going to be about. But this is optional here because we're running a little bit later than usual, and I wanted to make sure you had enough time to do the homework as well as to get started on your project. So the last part here is optional. If you want to work on it, it's perfectly fine, but we won't cover this material on until the very last lecture. Right, so one difference between the homework 5 and homework 6 is that there's this non-zero interest rate that's been included. So you need to adjust your code from homework 5 to also deal with this interest rate component, but it's not such a big deal. Okay, are there any questions before we get started? So if that's not the case, then we're going to be doing, we're going to be talking a bit about stopping times, right? So stopping times, those are random variables, right? So you go from omega, and you take values in the extended natural numbers. So 0, 1, 2, well, this is discrete time, so do continuous time. There it is. So in discrete time, you'll take values in the natural numbers, including infinity. In continuous time, which is what we're doing now, you take values in the closed interval all the way up to and including. This here is included. This is included, right? So the probability that tau is equal to plus infinity, this is bigger than or equal to 0. Right? And this can be strictly positive. So stopping time, well, first of all, it's a random variable, right? So it's a measurable function that goes from omega into these extended numbers, and it satisfies this curious property. So it's a random variable, has this such that what? Such that if I look at the set where tau is less than t, right? So remember, like this set here, this is shorthand notation for those omegas inside the central space, capital Omega, such that tau of omega is less than t. Is those omegas such that when I look at the level set for tau, I get something that is in ft. And this is true for any t between 0 and infinity, open here. Right, so that's the curious property. This is what a stopping time is. It's a random variable with this seemingly strange feature. And by far the main example is a passage time. Right, so this is you take tau. This is going to be the first time, say that this is the first time such that Brownian motion is, say, bigger than or equal to 1. So this is the smallest t such that bt is bigger than 1, right? So on a picture, you will have, right, our Brownian motion starts out here. I'll put in a ceiling. That's my bt. That's my ceiling. This here is 1. So I'm running my Brownian motion. And I have my path. And then at some point in time, this thing is going to potentially get up to here. And at that point, this here is my BT of omega. This is my path of omega. And at that point, this is what I'll denote. This is what I denote by tau of omega. Of course, you could also have a situation where you never get to the red curve. So you might have a blue curve. Can I find a blue pen? A blue pen? I can find a pink pen. So let me do a pink pen. So if I take the pink pen, right, so I'll have, this is the pink one, and it might never get up there. So this is my, if I call this first omega here for omega 1, then this will be tau of omega 1. And if I call the, it's very hard to see, but this is pink. This is my BT of, say, omega 2. In that case, for that omega 2, Brownian motion never crosses 1. And then I'll say that tau of omega 2, this is equal to plus infinity. This here is what it means. B2, that path, and never crossed the level 1. So crossed, it means that's what the word passage comes from. It never traversed through the red line. So this is the main example of such a random time. Say the first time it crosses over 1. You could also have other passage times. And they include, say, the first time that Brownian motion got bigger than, say, n, that will be a passage time for some n. It could also be, it includes this one. It could also be the first time that Brownian motion in, say, absolute value got bigger than n. That would also be a first passage time. You could even make it more tricky, and this is what we get in the, this is what would be relevant for us in the American put option case. This could be the first T, such that ST, drops below L of T for some function of time L. So there's no randomness about L, so L is deterministic. So the first time that the stock price drops far enough, we know that for put options, they become more valuable when the stock price is low. And so here we're saying that the first time that the stock price drops sufficiently far, this is our tau. So here were 4 examples of, well, this one here, the one with the 1, this is embedded in the first one. So here are more general, slightly more general passage times. Any questions on this part? So I think today we'll be content with just studying this object here. So there are pitfalls. So pitfalls don't treat stopping times as constants. So what I've seen is students write stuff like, I've seen students write and treat these random times as constants, right? So tau depends on omega. Tau depends on W. T does not. So there will be similarities, but these things are in general not the same. You should not treat these stopping times merely as another constant. Sometimes, so often we stop a process at a stopping time. Okay, so then we look at something like say xt min tau. Right, so what this here means is, this means that you're going to get xt of omega. Right? You're going to get xt of omega as long as t is less than tau of omega. And then when t is bigger, you're just going to get x tau. So on a picture, if we go back to that picture we had, the first passage time of Brownian motion. So as an example here, we will have that tau. So again, let me write out the omegas. Tau of omega is the first time where bt of that omega gets to be above, say, 1. So on a picture, what happens is, so as before, we put in the ceiling. And we run the Brownian motion. This one here is my Brownian motion. It gets up to here, and the Brownian motion continues. So this here is bt of omega. Wish I had a blue pen. I normally have a blue pen here. That was a blue pen, but that's my BT. So if I instead look at the blue one, would then be, if I stop at a time tau, so it'll move around, it'll be exactly the same. If we go in merry way, just like the pencil one. But the first time it hits, it's just going to stay flat. And it'll stay flat forever. The blue one is bt min tau of omega. So the blue one gets frozen. The blue one gets frozen at this point. So this one here is it freezes. Freezes, all right, freezes at t being tau. The first time it gets up there, it freezes. So the reason that I've seen students do this stuff here is that one should note just note that so tau of omega is a random variable here. Tau of omega is a random variable. Bt of omega is a random variable. But what happens when I do B tau of omega? What is the value of B tau of omega? Well, at that point, you're just going to get 1. So you take the Brownian motion, when it gets to the level 1, what is the value of BT at that time point? And that's equal to 1. This is equal to 1, and this is a constant. So it's kind of strange, right? You take two random components, you mix them together, and you get a constant. This is a constant whenever tau is finite. Right, so you get to the level. There are also some omegas, as we saw before. The purple line we never got to. We never got to level 1. So what we're going to be spending the next half an hour or so doing is we want to understand tau's distribution. So we want to answer questions like, what's the probability that tau is finite? What's the expectation? What's the probability that we actually get to this? So I picked the threshold 1. I could have picked 2 or 3. It doesn't really matter for what we're doing, but I picked the threshold 1. What's the distribution of that random variable? What's the probability of being finite? What's the probability? What is the expectation of this random variable? Any questions so far? There's like for those of you that took 621 with me, you will see that a lot of similarities with how we dealt with stopping times back then. It follows the same lines. There's like a method to attacking this, and it goes in a so often you need to use two theorems. So the first one, this is the dominated or sometimes monotone. You need to use dominated convergence. Right, so there'll be limits that have to be pulled in and outside expectations. So that one we're used to at this point. We talked about that a few times. The second one that we're not so used to, but you have seen potentially, is the Dupes optional sampling theorem. So that one is new. And Dupe optional sampling theorem says that if you take a martingale, for any martingale, say MT, if I stop it, the stop process MT min tau, this object is again a martingale. Right, so that stopped one, or the frozen one, that we could also, instead of saying stop, say frozen. And this theorem, the optional sampling theorem, this one here that's a new thing to prove that theorem, this is really where you need this property here over and over and over. So we won't go through the proof of Dupe's optional sampling theorem. You will find it in the textbook. You'll find it in the textbook. Right, so go to the optional sampling. So it's down here, optional sampling. So we're in 302. Yeah. Let's find this again. 342. There you go. So optional sampling, it says a martingale stopped at a stopping time is yet again a martingale. And here's the frozen process that we looked at. So you're taking a Brownian motion. So the first part here is a Brownian motion. And you stop the Brownian motion the first time it gets to say the level 1, and then you just freeze it afterwards. Like this little letter here is tau. That particular path of the Brownian motion path is going to continue, but the stop process, it freezes it right here. Here's a proof that he goes through why these passage times are why the stopping times. So I won't go through that. I'm just going to be using, this is in section 8 of Shreve. I'm just going to be using this result here to figure out what is toss distribution. Okay, so let me endeavor on that. So the tau that I'm looking at is the first time the Brownian motion crosses the level 1. Right, so again, tau, this is the first time. It's the first time, if any, that Brownian motion gets to be above 1. And I want to understand toss distribution, and the way that I want to do it is by looking at one of these functions that characterizes distributions. And so here, this random variable it takes values between 0 and infinity, right? So it's positive. And so I can use the characteristic function if I so desire, or because it's positive, I can use the Laplace transform. You do the Laplace transform. So what I'm interested then in is I'm interested in the mapping of the expectation of e to the minus and some coefficient, say lambda, times tau. I'm interested in the map that, since lambda here is a positive number, it goes into here. This thing here comes out because tau is non-negative. So this here is going to give me a number. This is going to give me a number between 0 and 1. And in particular, if lambda is equal to 0, in particular, if again lambda equal to 0, I'm just going to get a 1. Okay, so the Laplace transform is going to characterize the distribution of tau. We couldn't use the Laplace transform in these previous homework. We used the characteristic function back then because we didn't have this property that something was non-negative. We could also have put an I here. That would have given me the characteristic function. That would have been perfectly fine too. It's just the case that we have a non-negative random variable, so Laplace transforms are okay. So we want to understand, we want to compute what is this equal to. And the starting point here is going to be bring ourselves into using the optimal sampling theorem. Okay, so to use the optimal sampling theorem, we will need martingales. But so we could say, so we need a martingale. So some suggestions could be, well, we'll have BT. BT is a martingale. We could use the exponential of, what was it, sigma, let me put in square root 2 lambda, yeah, square root 2 lambda bt minus lambda t. Use this one or that one. Do both martingales or something else. The benefit currently, or we could use, or something else. I should maybe come up with another suggestion to what we could use here. You could also use an exponential. You put a minus sign here. Or something else. And so at least there are 3 martingales here: Brown in motion, exponential with a plus, exponential with a minus, or you can come up with yet a third, fourth one that you could try to get to work. For us, the good one to use is this one here. This one here is going to be a good one. This is going to be working. This is going to be working for us because it's positive. It's positive. Right, that B is not positive. This one is also positive. But the other one that is good is that if I stop it up to t equal to tau, I will have it's bounded. It's bounded, right? Because how do I make this quantity big? I make this quantity big by making BT big. But if I am up to this first time that it hits 1, then BT is less than or equal to 1. So it's going to be bounded by e to the root 2 lambda, right? This one here is positive because lambda, again, lambda is a positive number. So I throw it away. I'm going to get something that's bigger. BT up to that time point is going to be bounded by 1. So I'll get everything, this entire quantity here is bounded from above by this quantity. And that's not the case for this one over here. This one here, up to tau, up to t equals tau, this quantity is not going to be bounded because BT can go arbitrarily negative. BT can be arbitrarily negative. So if BT can be arbitrarily negative, this quantity here can be arbitrarily positive. So this one here is the one that's going to be working for us. B here, this can be arbitrarily negative as well. It cannot be arbitrarily positive up to time tau, but it could be arbitrarily negative. So putting in the exponential is going to get rid of the arbitrary negativity because the exponential is positive, and then the upper bound is going to come because BT is less than or equal to 1. So this object here is going to be uniformly bounded between 0 and tau. And that's what's going to allow us to use dominated convergence. Okay, so let's try to see if we can get it to work. So we can get it to work. So we have the martingale. We have the martingale, let me call it MT. This is this e to the root 2 lambda bt minus lambda t. So what else do we need to get this thing to work? I think we need one more thing. We also need the limiting behavior. So we also need the limiting behavior. So this is a non-negative. This is a non-negative martingale. Then there is another result by dupe. So dupes. So this is another big one, martingale convergence result. and this is what we have here, gives a limit. Gives a limit as t goes to infinity of mt. So this is just a warning. So this is just a warning to dupe not all martingales have limits. For example, BT up here, BT has no limit as t goes to infinity. Alice is asking a question, where does the root 2 come from? Yeah, of course. Of course. Yeah, so if I look at at an equation like this one, d, say nt is equal to sigma nt dpt, and I started out at 1. This one here has solution, and that's that form that we've seen lots of times. This is equal to nt is equal to n0, so that's a 1, then the exponential, and then it's sigma bt minus 1/2 sigma squared times t. And so all I'm saying is over here, I want to put a lambda. Okay, so I want to solve lambda is equal to 1/2 sigma squared. And this is the same thing as saying that sigma is equal to root 2 lambda. So I just want to have lambda here. If I want to put a lambda there, I need to put plus minus root 2 lambda over here. Okay, so we're itching closer towards actually figuring out what this Laplace transform is. But before we do it, let me just mention what the limiting object up here is. So you have a martingale. Like the expectation here, this is a non-negative martingale. So it's the word non-negativity that allow me to apply this result of dupe. So dupe has a number of elementary results on martingales of fundamental results related to martingales, and he has this optional sampling, and he has this martingale convergence theorem being the most prominent ones. And he, in particular, this martingale convergence says that if you have a non-negative martingale, it converges. So let me try to derive what this limit here is, and it's not terrible to do that. If I pick an epsilon, so this here is going to be convergence and probability, to be specific. So I pick an epsilon, and then I want to know what is the probability that mt is bigger than epsilon. Okay, I'll do that by inserting. This is basically the calculation we did when it was the Glasserman, the Brodian Glasserman material. We plug in this mt here. So this will be e to the root 2 lambda bt minus lambda here. It's bigger than epsilon. And then we do the same calculation as we did about an hour ago. We'll have p. This will go over to the other side, log epsilon. This is where we're using epsilon is strictly positive. And then we have lambda t here. And then I'll have root 2 lambda bt. then I'll divide over and get a standard normal. This would be P of BT. And then to get a standard normal, I have to divide by square root of T. What's the probability that a standard normal is bigger than log epsilon plus lambda T divided by root 2 lambda root T? So this here is a standard normal. So this here is my n evaluated at this mess, log epsilon plus lambda T divided by root 2 lambda root T. Okay, so I have equality everywhere. This is very similar to the calculation with Brody and Glasserman. And we have also done it in other, we also done it at other times. What I'm interested in, what happens with this probability here as t goes to infinity, right? We're trying to understand what the limit here is. And so I'll take the limit of these probabilities of mt being bigger than epsilon. Well, this will be the limit as t goes to infinity of this n of that ratio, log epsilon plus lambda t divided by root 2 lambda root t. So I'm going to send t to infinity. And the thing to look out for here, we have log epsilon divided by root t. T goes to infinity. This is going to cancel out. On the other hand, I'll have lambda t here divided by root t. Right, so the t wins when t goes to infinity. I'm going to end up here with n at I made a mistake somewhere. I made a mistake somewhere, right? This here is not, this is not n. But this is bigger than. This is bigger than, right? To get n here, I need to get less than. This equality sign here is not true, right? Anybody knows how to correct it to get the right thing? Very good, Alice. This is 1 minus. So I should have 1 minus here. I should have 1 minus here. So then here I'm going to get n at plus infinity. And n at plus infinity, this is equal to 1, so I'm going to get 0. So this means, so mt converges to 0 as t goes to infinity. So now we're getting a glimpse into a problem here. Right? So this is another warning. If I compute the expectation of mt, it's a martingale. So I'm gonna get that this is 1. In particular, if I compute the limit as t goes to infinity, I'm going to get m0, which is 1. But if I move that limit inside, I'm going to get 0. So this is why we have to be, when we're dealing with these stopping times here, we have to be a bit careful about these limits, because you very often end up in this situation where you can't do the swap. And so to the rescue comes these these convergence theorems that I had listed here. This is why we need these. This is why these ones in number 1 are needed, dominated monotone convergence. This is what allows us to not make mistakes of this sort here. Okay, we're still not there yet. We have identified the limit. This thing here is as 0. So we have a martingale. It has expectation 1 for all t. It converges. Unfortunately, it converges to 0. So we have to be careful when we do the expectation and limits. And we're going to be doing that exactly now. So to calculate this Laplace transform that we're interested in, what we're going to be doing is we'll start out by saying, so to get the Laplace transform, we stop m and take the expectation. So mt min tau. This is a martingale, that's dupe. So this is going to be equal to m0, which is equal to 1. This is dupe. This is dupe's optional sampling. And now comes the harder part. We have to take the limit. We have to take the limit to get rid of the t here. Okay, so dupe's optional sampling, this thing here implies in particular that when I take the limit as t goes to infinity of the expectation of mt min tau, I'm going to get my 1. And what I really want to do now is to put this limit inside. Okay, so to move the limit inside, to move this thing inside, we use dominated convergence. We use dominated convergence because, well, m is positive, so we obviously have this is true. And then we use that other bound. That we have here, that up to time tau, this quantity here is bounded by this e to the root 2 lambda. So this quantity here is bounded by that quantity. So this here is bounded by e to the root 2 lambda. So this is a constant. This is a constant. There's no t dependence. We can use dominated convergence to pull the limit inside. And if we do that, we're going to get 1 is equal to, and then I put the limit inside now. The expectation, t goes to infinity, mt min tau. And we have to work out what this thing is. Okay, so let me take it slowly. This expectation, let me break it up into 2 parts. T goes to infinity. And then I'll split it into when t is less than tau, I'm going to get mt. Maybe I can split it up into, I'll split it up into when m t min tau, and then I'll say when tau is finite, plus the same thing when mt min tau, when tau is plus infinity. So what will I get is, if tau is equal to plus infinity, t is finite. This thing here, this is going to become mt. And over here, tau is finite, okay? And then I'm going to take the limit as t goes to infinity. This is going to give me, what is it going to give me? It's going to give me tau is finite. Okay, so there's a finite number, and I'll take t to infinity. This is going to give me m tau times the indicator for when tau is finite. On the other hand, when I take t to infinity, I'm going to get the limit of mt. Okay, so that's going to give me 0. This was my m infinity times when tau is equal to plus infinity. Right, but this one we just did, that was equal to 0. So I'm just left with this guy. So I'm just left, this is a 0. This thing here is bounded by 1, so I can forget about this. I get a formula for m tau expectation, provided that tau is finite. And let me insert what m tau is, and this goes back to Alice's question about where does that root come from. And let me write out what this here is. This is e to the root 2 lambda b tau minus lambda tau, provided that tau is finite. But if tau is finite, then b tau, this is going to be equal to 1. We already had that this quantity here, when tau is finite, this is going to be equal to 1 when tau is finite. So I'm ending up here with a constant. This is going to be e to the root 2 lambda. E to the root 2 lambda. Then I'll have an expectation, e to the minus lambda tau. And then I'll have this indicator, tau less than infinity. All that stuff is going to be exactly equal to 1. And then I can move the constant to the other side. I have a 1 over here. This will tell me that the expectation, e to the minus lambda tau, indicator tau finite, but this here is equal to minus exponential of minus 2 lambda. In particular, we can take lambda and pass him to 0. So now, because this quantity in here, e to the minus lambda tau, indicator tau less than infinity, this quantity here, this is bounded by 1, and it's positive. We can again use a dominated convergence. We can again use dominated convergence. So we'll take a limit, we'll pass lambda down to 0. We'll pass lambda down to 0 of this expectation here. Indicator tau is finite. We'll see that this is equal to the limit over on the right hand side, lambda down to 0, e to the minus root 2 lambda. Dominated convergence is going to give us this equality sign that we can pull the limit inside. We can pull the limit inside. Right, that was dominated convergence. And on the other hand, exponential, this is a continuous function. We're just going to get exponential of 0. So this is a 1. And inside here, when lambda goes to 0, it's going to be the same story. This one here is equal to the expectation of the indicator of tau being finite. So that's going to be 1. But of course, the expectation of an indicator, this is my probability of the set. So to answer the first question, the probability that the Brownian motion hits the level 1 in finite time, and this is equal to 1. So that's good news. Brownian motion hits the level 1 with probability 1. it also allows me to use this formula here to say that, well, the set I have downstairs, this really has mass 1. So let me call that star. So star gives E of minus lambda tau, indicator tau finite. This was the formula we had, was root 2 lambda, right? But I can delete this one here, has mass 1, so I can write this here as e to the minus lambda tau. This one here is because the probability of that set is 1. And that's the Laplace transform. This is Tau's Laplace transform. So we succeeded in calculating Tau's Laplace transform. And of course, if we have the Laplace transform, we can get at the moments. So by taking derivatives. We get Tau's moments. We've done that before, and the problem here, of course, is on one hand I want to take a derivative of this thing here with respect to lambda. Okay, so I can do that. The derivative with respect to lambda of this e to the minus root 2 lambda. How would I get it? See if I can do that. So it's a composed function, right? So it's an exponential. I'm going to get the exponential back. And then I have to take the derivative. I have to take the derivative of what is I have to take derivative of what is inside. So I need a derivative with respect to lambda of root 2 lambda, and then there's a minus sign. See if I can do this. So there's a square root 2, so there's a square root there. This is a half. Now I have a minus a square root 2 out there. The derivative of a square root is e to the minus root 2 lambda. The derivative of square root is going to be a minus a half coming down. That will be half coming down, so we need to divide by 2. And then it's going to be 1 over square root lambda. And as you can see, this is problematic if I want to evaluate this at lambda equal to 0. So there's no derivative at lambda equal to 0, right? Because we're dividing here by dividing by 0. So this is going to imply that the expectation of tau. Any guesses on what that's going to imply for the expectation of tau? So if the Laplace transform doesn't have, if it doesn't have a derivative, then I can't compute the moment. So what do you think the moment is then going to be? Let's try it again, right? We should have, normally I'll compute moment, if I have one of these characteristic functions, a Laplace transform or the characteristic function or the moment generating function, I'll compute derivatives to get the moment. So here's a situation where when I compute the first derivative, evaluated at 0, it doesn't exist. What would you think that implies for the moment? So maybe if you go back to an earlier homework, we can get some inspiration there. We go back to homework. Is it homework 3? No, homework 2. We go back to homework 2. Yeah, remember this one, the characteristic function here. What happened here? What happened when you didn't have differentiability of the Fourier inversion theorem? What does it imply that if you didn't have a derivative for the Cauchy, so in the Cauchy case, you didn't have a derivative, and so what did that imply for the moments of the random variable? You don't exist. That's right. You're infinite. So here we have exactly that situation, right? There's no derivative. This implies that the first moment, and therefore all the moments, d equal to plus infinity. This is as in homework 2. So what we have here is a random variable that has this property that it's finite with probability 1, but it doesn't have expectation. This is as the Cauchy in homework number 2. It's a very similar situation. That passage time that we're dealing with here, it's finite, so the Brownian motion will get to that level, but the expected time it'll take the Brownian motion to get to the level is plus infinity. Okay, I think this is all I wanted to say for today. As I said in the beginning, this is a short lecture because I have a meeting coming up, and I also want to give you guys some time to work on the homework and start thinking about these projects that are going to be due in a couple of weeks. Are there any questions on today's lecture? Okay, so there are lots of questions today. I really appreciate all the questions. This is awesome. Tomorrow morning, there will be office hours from 9 to 10. If there are no other questions, then this is the end of today's lecture. There will not be a second half. And I hope to see you guys tomorrow. And if not, I'll see you guys next week.